So now let's move on to the next speaker, who is Rogelio Ortigosa. He's an associate professor in Cartagena, in Technical University of Cartagena in Spain. And also he's an honorary research fellow from Swansea University, where he did his PhD in the Sinkeveen Center for Computational Engineering. Also, he's an expert on finite element formulation for numerical modeling of smart electroactive polymers. For this research, he received several recognitions. And currently, he's involved in the design optimization of multifunctional materials, including electro-magneto-thermomechanical interactions. So thank you, Rogelio, for coming.
Okay. I'm sorry, I'm going to take a glass of water. So thank you, Jesus, for your introduction. And thank you to the organization for inviting me to this nice conference where we are currently enjoying all the talks. I really enjoyed the talks yesterday, and I'm super pleased with your talk. I learned a lot of things. But I'm sorry to disappoint you because I'm not going to be doing topology optimization of microstructures. Okay? Okay. So, but I hope that this is the only disappointment through my talk. So in my talk, I'm going to be talking about smart materials. These are materials that, when subjected to external stimuli, it could be an electric field, magnetic field, you can see plenty of stimuli there, thermal, chemical, etc. Well, these materials can deform, and they can change their stiffness. I'm going to be focusing on two types of these smart materials, electroactive and magnetoactive. So in electroactive materials is an electric field that drives the deformation of the solid. Mokarran yesterday gave a very interesting talk on electroactive materials, particularly on dielectric elastomers, and he gave many examples of energy harvesting applications, okay? With regards to magnetoactive materials, well, in this case, it's the magnetic field, which is going to drive the deformation of these deformable solids. And Daniel, here today in the audience, is going to be giving a very nice presentation on biomedical applications of magnetoactive materials. But like I said, I'm going to be focusing on these electroactive and magnetoactive materials. And the interesting feature of these materials is that they are very soft. You will see that they are very soft, and hence they can deform a lot when they are subjected to electric or magnetic fields. And this is what makes them very appealing, very interesting, very attractive for applications in the field of soft robotics. Okay? So the objective of my presentation is actually to make use of computational tools such as topology optimization, optimal control, machine learning, but not for design. Okay? That has to be clear. For the design, okay, of smart materials when subjected to electric fields, magnetic fields, from a computational perspective, okay? So this is actually the layout of my presentation. So first I will cover very briefly the topology optimization, the design through topology optimization of electroactive materials. Then I'll move on to magnetoactive materials, and then I'll jump into a recent line of research that we have started with our postdoc when you consider these materials, exploring these materials actually in fluid environments. So we'll be doing fluid structure interaction of smart materials. So I'll start with the topology optimization, the design through topology optimization of smart materials, electroactive materials, sorry. Within electroactive materials, I'll be focusing on dielectric elastomers, which is exactly the type of material that Mokarran was covering yesterday. And he very well said that these are polymer materials, rubber-like materials, incompressibles, that when sandwiched between electrodes, they are going to decrease their thickness because of Coulomb forces, and they are going to expand in area. Okay? And they can deform a lot, and you can have applications in soft robotics. For instance, you have this soft gripper, you have this other manta ray propel through the actuation of electric fields on the flaps of this device, and of course, energy harvesting applications that Mokarran showed yesterday. I come from the field of computational mechanics, like my colleagues, and I use computer for the simulation of these materials, okay? And in the end, we like implementing our codes, our numerical algorithms in our in-house platforms. And in the end, if I want to simulate this, I need to have a mathematical model of these materials. And the mathematical model, I'm not going to go into the detail of the equations, just to let you know that we have two coupled physics. We have the electrical physics, and those are represented by the Gauss law and Faraday's law. And then we have the equations for the mechanics, which is the conservation of linear and angular momentum. And these physics are coupled through a constitutive equation that ideally has to be provided by experiments, and that is going to allow us to define something called a strain energy density, which is this psi function. Hopefully this is going to work. Yeah. There you go. This is this psi function that appears here, which encapsulates the constitutive information, the constitutive law of this material. Just to mention that it is a non-linear constitutive equation in terms of deformations and electric fields. Okay? So we have a couple of partial differential equations, non-linear, and we are going to solve them discretizing in space using finite elements. Okay? And this is a very nice example of what we can do simulating these materials. So we apply voltage on these materials, and what you can see on the bottom is actually results from our in-house platform, electrically induced wrinkles on these materials, which, on the other hand, also appear on the experimental lab. Okay? But the question is how to design these materials. So you saw that you place on these materials, you sandwich them between electrodes, and then you get contraction in thickness and expansion in area. But in reality, we are interested in getting more complex electrically induced deformation modes. We would like to have out-of-plane deformations like the one shown here, changes in curvature, etc. And in order to achieve that through topology optimization, we are going to pursue two approaches actually proposed by Professor David Clark in Harvard University. So he proposed two very clever examples, two very clever approaches. The first one, you can see it, hopefully, I'm going to be able to point correctly. There you go. No, this is the first approach. And in this first approach, you have these, I'm colorblind, so it's very difficult for me. So you have the red one, the red layer, or brown, I'm not sure. Okay. There you go, sorry for this. There you go. So the red layer is a dielectric elastomer, and it's going to be sandwiched between electrodes. You're going to apply an electric field, and then you're going to place passive layer of stiffeners on top and bottom. And the idea is to remove material so that when I apply electric field on the dielectric layer, this is going to deform out of plane. Okay, so this was proposed by Professor David Clark. Alternatively, there is another approach, which is the one below. Well, don't use stiffeners. In this case, you generate a heterogeneous distribution of electric field within the material. And in order to do that, what you need to place is electrode regions, these things here that I'm not able to point, sorry. These things here, this is better. These things here represent electrode regions, and you need to design the shape of these electrodes in order to generate this heterogeneous electric field distribution. And hence you can get these out-of-plane deformations that you are seeing here. I'm going to start describing this one very briefly from the mathematical standpoint. Okay? So again, I have a mathematical problem that I'm going to try to solve with using topology optimization. I'm not going to design the dielectric layer, which is the gray one here. Okay? What I'm going to try to do, and the objective is what? I'm going to apply. This is initially planar, okay? I'm going to apply an electric field on this material so that I want this to deform in a specific way. I want this to attain this target shape. So I want to minimize the distance to a specific target configuration. How am I going to do that? Well, somehow I'm going to remove material, like Niels said. I'm going to remove material from this layer and this layer so that when I apply the electric field, the material deforms in a specific way. In order to do that, we make use of a pseudo-density, like Niels said very well before. We make use of the SIM method, solid isotropic method with penalization. So, and we introduce a pseudo-density variable, which is this one that you can see here. And that one is introduced in the layers of the passive material, the stiffener here on top and bottom. So that when this raw variable takes values of 1, it's going to take values between 0 and 1. When it takes a value of 1, it means that you have a stiffener. And when it takes a value of 0, it means that you remove material. Okay? We implement this within a grading algorithm, and we let the algorithm evolve. This is iterative, like you could see in Niels' presentation. And eventually, you can see some examples. Very simple examples. You can get more complex electrically induced deformations, but this is for illustration purposes. So imagine that you have, again, this device here, this dielectric elastomer in red, and then the objective is to get a deformation when you apply the electric field such that you want this point B, you want to move downwards to a specific place, and the point A, you want it to move upwards, and then you want these to replicate in the circumferential direction, okay? Then if you apply topology optimization to this problem, the result that you get is actually you need to place the stiffness on top and bottom layers like this is dictating, okay? And then you apply the electric field and you get exactly the target shape morphing configuration that you prescribed at the beginning. Slightly more complex electrically induced deformation. In this case, on the right, you move this point downwards. Now the point C goes upwards and A goes downwards again, and then you repeat it circumferentially. This is the result that the topology optimization algorithm is telling us. This is the way you need to place the stiffener on top and bottom layers, okay? Now we move to the other approach that Professor David Clark proposed. In this case, we don't have stiffeners, we are going to have a multi-layer device. So we have several layers of the electric elastomers. This gray thing represents the electric elastomer. And in between, I'm separating the layers. In between, I'm going to intercalate electrode regions. So in here, I'm going to apply a potential. In this one, I'm going to apply a different potential. It's actually the same potential, but with different polarity. So I'm going to be alternating the polarity of the electrodes. But I need to design the electrodes that I'm going to place in those regions. And the way I'm going to do it is following the following approach. So imagine that you have this device. I'm zooming the thickness direction. This is much thinner, okay? But this is for visual purposes. So imagine that I have 6 layers of material, and in between I'm going to place like 5 regions where I want to design, surface regions where I want to design my electrodes, okay? I'm going to apply voltage on this one, on this one, on this one, on this one, on this one. And I want to design, like I said, the electrode. In order to do that, I'm going to make use of a phase field on each of these surface regions. And that phase field is going to take values between 0 and 1. 1 means that you have electrode. It would be this red region here. So you have electrode, and blue means, 0 means that you don't have electrode. This way you have like a smooth representation, a smooth representation of the boundary, where you have intermediate values of the phase field. So the optimization problem is eventually the same. You want to minimize an objective function, a merit function, which is what? Well, you are going to apply electric potentials on these regions, okay? On the electrodes that are going to be designed on these regions. And eventually, you want that the electrically induced deformation is something that you prescribed, okay? So you want to minimize the distance to that target configuration. And then, well, what we need to do is to evolve somehow the phase fields representing the design of the electrode on each of these surfaces. And the way we do it is by using an Allen-Kahn type of evolution equation for these phase fields. And as you can see in this type, well, this type of evolution equations comes from the field of phase transitions and also in fracture, okay, in fracture mechanics. And you can see here how we make use of a double well potential in order to force the phase fields in each of these regions to fall within 1 or 0 values, okay? This is the way with a double well potential to enforce reaching 0 or 1 values. And this is a very simple example that actually explains what we are doing. I'm going to show you a video, but first I'm going to explain. This is a very similar electrically induced deformation shape to the one that I explained before. So imagine that you want to move point B upwards to a specific location, and then this one downwards, and so on and so forth, to specific locations. When you apply electric potentials, where? Well, you have now 6 layers of material, and then 5 regions of electrodes that need to be designed, okay? So you will apply the potential, and you want this target configuration. So what is the design of the electrodes? You can see that actually on this video, not on this one. On this one. So in every topology optimization algorithm, we start with an initial guess. In that initial guess, you have somehow 1s and 0s, okay, in each of the electrode regions, and eventually you converge to a solution so that this is actually the design of the electrodes that you need to have in order to have this electrically induced deformation. So this is what I wanted to say regarding design in the context of electroactive materials. Now I'm going to move to magnetoactive materials. So this is a work that we are, this is actually an ongoing work that we are carrying out with Daniel. Daniel is involved in many things in the conference, but also in many talks, so he's everywhere. Thanks to him. So specifically, we are going to be focusing on a specific type of magnetoactive materials, which are called hard magnetic soft materials. Okay, these are polymeric materials. They are incompressible. They are comprised of a very soft matrix. Okay, and within that matrix, you place magnetic particles. These particles are initially distributed isotropically, and then you apply a magnetic field until these particles get oriented. You can see it here. They are oriented, and they get a remnant magnetization, and that magnetization is permanent. So if you remove the magnetic field, the particles are still aligned, and they are still magnetized. Okay? So you can see what happens in this device here. It has been magnetized in this direction, uniformly magnetized in this direction, and then we have removed the magnetic field. And once you remove it, the particles retain its magnetization. But what happens now is that if you come back now with a second magnetic field, this one, in the opposite direction, there is going to be an intertwin. There is going to be an interplay between the remnant magnetization and this second applied magnetic field, so that this one is going to try to align the remnant magnetization with this second magnetic field. So eventually, what it's going to try to do is to move it to this side, to the left side, and then you're going to have this bending type deformation. Okay? So these are magnetically induced deformations on the solid. But now, in this case, in this particular case, the magnetization has been distributed uniformly on the solid. So what would happen if we were able to design the spatial distribution of these orientations of the random magnetization? In that case, we could have more exciting magnetically induced configurations, like the one that we have here. This is the objective of the second part of the talk. But first, I need to cover very briefly some things regarding the computational standpoint of hard magnetics, soft materials. Okay, so again, I'm going to consider a partial differential equation for these. The mathematical model is represented by a partial differential equation, and the relevant thing is that we have, again, in this problem, a strain energy density, which is nonlinear, and it's typically decomposed additively into something passive and something coupled. This term here is actually responsible for that interplay between the remnant magnetization and the second magnetic field. Well, the relevant thing for this presentation is actually, and this is the contribution from my colleagues at Universidad Carlos III, from Daniel, is that this passive response usually, when you have magnetized the material, the particles within the material are aligned. So the material is no longer, even when it's passive, when it's not actuated, the material is not isotropic. It's transversely isotropic, actually. And you should include that anisotropy into the passive response of your material. And this is what they proved in the laboratory. So basically, they considered two materials, soft matrices, the Doe and Silger. And they embedded particles within this material with different concentrations. They carried out a uniaxial tension test, and they did it for the material without prior to magnetization and magnetized in different directions. Okay, there is no magnetic field in these experiments; they are already magnetized, and the fact that the curves don't lie on top of each other is actually telling you that the material is anisotropic; it's not isotropic. Okay. So they carried out these experiments, and these experiments were good for us in order to derive a strain energy density, which is what I need in order to conduct simulations. Okay? The way I created my strain energy density was through machine learning using neural networks. Okay? So I created a neural network with whose inputs were invariants of the deformation, and in order to obtain the biases, weights, and so on of this neural network, of my strain energy density, I minimized, essentially, you can see it here, the stress data provided by our colleagues in the lab, and the stress data derived from this energy, from this strain energy density. So in essentially, it's a Sobol type neural network. Okay? So now we can do simulations. They prove that the effect of anisotropy is important in the lab, and we also demonstrated that in simulations. For instance, you have a simulation here where you pre-magnetize the particles in a radial direction. You fix the inner radius, and then you apply a magnetic field downwards. There is a mistake here. This is downwards. Okay? And then what happens is that if you consider the passive response being isotropic or being anisotropic, at a certain extent, the responses of both can be qualitatively similar, okay? But in this particular example, there was a point beyond which wrinkles started to show up, to appear. And then you can see clearly that the wrinkling pattern exhibited by considering or not considering or neglecting the anisotropic contribution was actually quite different. So we are capable now of simulating these materials, and we can integrate these into our topology optimization framework. Again, we need to formulate this as an optimization problem. What I want to do is I want to apply this field, this BA field, and applying this field on this material, I want the material to move to the form, to attain a target shape, okay? According to what? Well, the topology optimization algorithm is going to tell me in what places I need to magnetize, in what places you are going to magnetize material, you are not going to magnetize the material, and this is done by introducing this pseudo-density field, which is actually regulating magnetized and non-magnetized material, and also in those regions where you magnetize the material, in what directions. So the direction of the magnetization is also a design variable in my problem. Okay? And here are some preliminary examples that we obtained with our colleagues in Carlos III. All the samples, all these designs were initially plain, okay? And then we said, okay, well, let's see what magnetization orientations we need to prescribe in order to attain a specific target configuration. We wanted to get this shape configuration. We run our topology optimization problem. We pass this data, this information to our colleagues in the experimental lab. They magnetize according to the guides of the topology optimization algorithm, and then they again apply a magnetic field, and they get the magnetically induced deformation, which is pretty similar to the one that we are obtaining numerically. Okay? 5 minutes? Okay, then the third part, which is the most challenging part. So how do these materials behave in fluid environments? Like I said, we just started this line of research, and it's the most challenging one that we have ever faced. We wanted to explore, like I said, these materials in fluid environments. There are nice applications nowadays of these materials in the lab. So there are people which are experiencing with dielectric elastomers, not robots in fluids propelled through dielectric elastomers, okay? But I want to simulate this from a computational standpoint. And there are many challenges here. The challenges are, well, if previously you had a set of nonlinear PDEs, coupled multiphysics PDEs, now you have the fluid. You're adding more complexity, and it's a dynamic problem. So things are starting to build up. So you may think of using machine learning in order to leverage the computational cost of this problem. So imagine that you have now these soft materials in a fluid. Don't apply electric or magnetic field. If you have them, what's going to happen? They are flexible, right? So in this example, which is actually a benchmark in fluids, don't apply anything. This is a flexible material. We have this ball here, which is rigid. You have the fluid coming from the left to the right. Initially, nothing happens, but then vortices start shredding, and then you have this oscillatory movement of the solid. And it's going to be oscillating quite a lot. This poses a challenge because now the partial differential equations that I'm going to be solving barely fit within the slide, okay? So we have, again, the nonlinear equations for the solid, for the mechanics, the electro. If we apply magneto, these equations are not going to restrict to the solid. They are going to be solved also in the fluid. And then we have the equations for the fluid dynamics, okay? I'm not going to go into the details of the computational strategies used because I don't have time, but just to mention that here you can see that you have the fluid, you have the solid, and there has to be a coupling, and that coupling comes and happens in the interface, okay? The interface is going to give you quite a few problems, okay? Anyway, so we are starting to run and exploring some simulations in order to gain some insight into what's happening, what's going to happen. So again, this example in which the fluid comes from the left, you don't apply any electric field, the material is obviously going to bend to the right. But what happens if we now apply electric potentials in different configurations? Well, in this case, we apply electric potential across the thickness, you get elongations. In this one, if you apply it in the thickness, in one part, in the right part, and in the middle one, not touching the one on the left, you start getting a bending to the left, and then you can compensate actually the deformation of the solid. And actually, if you find the right combination of potentials, that one is going to remain perfectly straight, okay? And how many minutes, Jesus? 2, okay, cool. So this is a very challenging computational, okay, now I can relax. I'm gonna finish on time. Very challenging. This is 2D, but we are also solving 3D, okay? But what happens if you want to solve the inverse problem, which I was mentioning, which is, what potential do I need to put, what electric potential do I need to put in order to let this solid move in the specific way I want it to move, okay? This is what we are doing. And for that, it is very convenient to generate a digital twin. We're exploring not just neural networks, but other methods, a digital twin of the solid which is immersed on the fluid. Okay? We parameterize the response of the fluid in terms of the potentials that you are going to place in discrete places in order to, well, somehow leverage the computational cost of this challenging problem. And that was all, okay? I just wanted to share with you my thoughts. Perhaps I'm wrong, perhaps I'm right. After talking with Daniel, it seems that I might not be very wrong. But what I think is that you cannot just focus on one spectrum of the field. I think that the synergy between computational simulations, experiments is actually beneficial, and it's actually the way to push the advance into the design of these materials. Okay, thank you very much.
Well, thank you, Rogelio, for this nice presentation about the use of optimization techniques for multifunctional materials. Is there any question in the audience about this talk?
Good morning, Rogelio. Was a really nice presentation. My question is more regarding the size of experiments. I think that most of the tests are making in small device or small robots. Mm-hmm. I was wondering about to escalate for big robots. Bio-inspired rod for sure. For example, in the case of manta rays, that they have like very elastic movements, flapping movements. So if we can maybe think in few years or months, or I don't know, to use this approach to move this kind of robotics device or systems.
To a larger scale, you mean?
Yeah.
Well, I'm not sure. To be honest, I'm not an expert on that side. My expertise is on computational mechanics. If someone from the experimental side has any insights on this, I have my doubts because, I mean, with regards dimensions, in order to, for instance, for the case of, especially for the case of electroactive materials, in order to get deformations, appreciable deformations, you need very, very small thicknesses. And typically the devices are, in length, are centimeters, all right? So I don't see now moving to a scale of meters, but perhaps I'm wrong. Like I said, my expertise is not that one. But thank you for your question.
It's okay? Yeah. Just trying to answer in this question, just my feeling. Is that the main problem here when you want to go to large scales is that you need huge sources. So we probably need like huge sources to create a magnetic field or a strong electric field in a confined space. But then, well, we're going to present later a little bit, but you can think also something that Rogelio saw, is that it's not only, for example, for the magnetic problem that you need to actuate directly. You can also make advantage from the passive interactions. So maybe the idea now is that as you understand how everything is going, you have a remanent magnetization. So as the things are deforming, they are interacting. So in that case, you can program some responses without the need of the external field. So I will say that that's great for small things that we are able to interact. And if you want to go for larger interactions, maybe the idea is to try to find these kind of things. or design stuff just based on instabilities. So you made your design super close to a given or bifurcation scenario where you only need just a click, and then the whole thing collapses and the whole thing changes drastically. So my feeling is that if you want to focus on realistic applications for larger scale, these are the two lines I can think about.
Is there any more question? I think that.
Well, it's going to be super quick. Thanks for the talk. It was very, very nice. I was just wondering, like, when you are creating these magneto-active materials, have you thought about, okay, you're imposing different magnetic fields, which is very great to have these deformations or different modes of deformations. Have you thought of not having the particles or the magnetic active element homogeneous, but rather having some patterns and then again applying these magnetic patterns, so like you would have more complexity in your system?
No, to be honest, we hadn't thought of it, but this is a problem that we can formulate and we are happy to address. Yeah, that's a very nice idea. Yeah.
Cool. Thank you.
Collaboration opportunity.
Any more questions? I think just one.
Very, very nice talk, Rogelio. I had a question on your model I had a question on your model on the DEAs, right? So usually these actuators, you need to have some kind of like rigid frame to have some pre-strain for that, right? So how can you design those weird kind of subtle geometries and some points coming up or down? How do you account the pre-straining for that on your model?
Well, I have the answer for that. So in 2016, I think it was Professor Clark. He proposed a different approach in which you have a multi-layer concept. So in this multi-layer concept, you place electrodes not just on top and bottom, which is the classical setting, right? You place them in between. If you place them in between, it's when you don't need pre-stretching, which is what you are referring to. You don't need pre-stretching, and you don't need such high electric fields in order to get these curvatures. All right. But it's inserting electrodes within the material.
But do you still get like a good work output out of those?
If I didn't hear it.
Do you still get like high forces out of that?
I haven't measured forces, to be honest.
Okay. Cool. Thank you.
Thank you.
So let's thank again Rogelio for the presentation.
Thank you.